In the second session of introductory robotics training, we are at your service. And in this session, we want to introduce you to the types of sensors that are widely used in robotics. And of course, apart from robotics, they are also widely used in various applications, such as the Internet of Things. So, by knowing these sensors, you can implement many projects. So let's see what sensors exist and what purpose these sensors can be used for. The first sensor I want to introduce to you is infrared sensors, which are used for various purposes in robotics, such as distance detection in robotics, obstacle detection in robotics, or line change, and similar issues. Infrared sensors are usually in form of a receiver and a transmitter. In this image, you can see the sensor and infrared connection, which consists of a receiver and transmitter. One of these LEDs is an infrared light transmitter, and one is an infrared receiver. So let me explain a little more about this sensor so that its operation becomes clearer. An infrared emitter LED, which is actually an LED bulb, just like regular LEDs like the one you see here. The main difference is that instead of visible light, it emits light in the infrared frequency, which is invisible to the naked eye. Of course, you can easily observe the light of these types of LEDs using a camera like a mobile phone camera. In this short video, I turned on an infrared LED, observed its light. You see, I don't actually see this light with my eyes when I'm filming. It's only visible in the camera, and that's why you're seeing it too, because the camera sees the light and makes you see it too. You can see it in the image. Now we come to the part that is the receiver. The receiver, for example, is actually a type of transistor known as a phototransistor. You might be saying to yourself, well, it looks like an LED. While transistors have that shape, but this is also a transistor, and it's different from the transistors you've seen so far. In fact, this transistor is made to resemble a diode in that it has a transparent part so that infrared light can reach it. Well, this phototransistor also has two terminals, which are kind of like a collector and an emitter, but its base terminal is inside this transparent part, and instead of being excited by voltage, it is excited by infrared light. Of course, I should open a parenthesis that we have different phototransistors, and even many phototransistors or phototransistors with light are actually excited at their bases, but in this model, since my goal is infrared, this type of phototransistor, the transistor is made in such a way that its base leg is excited and activated by fluorescent light. In fact, when infrared light reaches the sensor or phototransistor passes a voltage, and the greater the intensity of the infrared light, the more light passes through. Thus, by putting together an infrared light transmitter and generator and an infrared phototransistor, we have an infrared sensor. Now let's see how this infrared sensor works. To answer this question, I must first briefly explain how sensors work. It is better to know that when we talk about the output of a sensor, it means that the sensor is a voltage at any value. It outputs voltage in different forms, such as DC voltage or voltage in the form of PW, which is actually a type of wave. This voltage reaches, for example, an IC or processor, which then performs a task based on the programming. So in any case, sensors output voltage in different forms and from different sources, so anything that can output voltage can be used as a sensor. In this infrared sensor, it also works as I will explain to you in this image. Imagine that we want to recognize a meaning using this sensor. Well, in this case, we have to put the sensors, the receiver, and the transmitter in such a state. In this case, the circuit structure is simple, of course. I will explain it to understand the issue because the circuit structure is more complicated than this. In this case, the circuit structure is as follows. A voltage is applied to the input base of the receiver or infrared or the phototransistor, but it does not pass to the other side until the infrared light reaches it. On the other hand, the one LED, that is the infrared transmitter, is on and is shining light forward, which is not reflected as long as there is no obstacle in its path, but as long as there is an obstacle in its path, the light hits the obstacle and actually blocks it, and some light is reflected towards the receiver. In this case, the light that hits the receiver, this phototransistor starts passing voltage, and this voltage that passes through this receiver reaches an IC for use and detection, and thus the IC, as programmed, detects that there is an obstacle in the way. Now, the closer the robot gets to the main, the intensity of the reflected light increases, and the voltage in the receiver pass increases, And this is how it is determined how close the robot is to the main. So using the sensor, both the presence or absence of the main can be detected, and the proximity of the robot to the main. Well, this was a brief and practical explanation about the functioning of the sensor and the functioning of the infrared sensor that you saw. You also know that now sensors are actually types of modules that give voltage and a signal to the black eye of the central processor. And we started a brief explanation with the sensor in the red module so that you can better understand how sensors work. So you have seen how useful a sensor is, and especially the infrared sensor, how much it is used in robotics, and in fact, it is widely used. We will use each of these sensors that we introduce and practice in the next series, and when building different robots, and you will learn from them well. So now, our only goal is to recognize these sensors and their operation. That is, here I want you to know only the important and most useful types of sensors so that when we start building, for example, a robot, we know whether we need any of these sensors at all. So what? We considered for our robot, and what sensors are there? Are there any such sensors at all, or are there many? Hopefully this introduction to sensors will help you. So the next sensor that I want to introduce, which is again one of the most useful, is the ultrasonic sensor, which has exactly the same operation as the previous infrared sensor, with the basic difference that it uses sound and sound waves, which you can see in this image the shape of the entire ultrasonic sensor module. This sensor also has a transmitter and a receiver of sound waves in the infrared band, which is naturally, we cannot hear the sound of the infrared, and it is not in the range of human hearing. This sensor is used to detect distance, detect obstacles, detect objects, and such things. In robotics, this sensor is also used more for detecting obstacles and detecting distances, as well as detecting various types of objects. Their operating voltage is usually between 33 and 5 volts, which most often works with 5 volts. But the engine speed detection sensor, the next sensor is a sensor that is used to detect movement or engine torque, which allows us to detect the engine speed well. For example, how many revolutions per minute an engine is rotating. So detecting the engine speed has many carburetors in robotics. You see the image of this sensor, and you should know that this sensor model that you see works based on the infrared sensor, and in fact the same basic infrared sensors that we introduced are used in these sensors. So you see that even that strange sensor is not just for detection and distance, and is also useful for other uses. This motor speed detection sensor works in this way, that the infrared transmitter is located in this part and the receiver in this part. Now this sensor is installed on the motor in such a way that a small blade that is connected to the motor rotor rotates between these parts. By rotating the blade, which causes the infrared light to continuously disconnect and reconnect, the motor speed can be detected, meaning that the more the number of disconnections, the motor is rotating at a high speed. And the slower the disconnections, the motor has a lower speed, and this creates a cycle as an output signal that you will learn well with the programming and the nuances of this cycle in the next series. It is easy to show the movement and the motor on the screen, for example. We can make that cut off in such a problem of product, and in fact, based on this, let's determine the number of revolutions of the motor per minute, so that, for example, our circuit can show the movement and the motor on the screen. So our next sensor is the camera. Well, many of you may be surprised that we call the camera a sensor, but it really is a sensor. The sensor area that receives the complete image of the environment. When you get into programming microcontrollers for robotics, you will see that in programming, when we want to receive the camera image, we write sensor, because there are cells inside the cameras that receive the amount of ambient light, colors, and everything that makes up the image, which in technical terms are called CCD, or CMO sensors inside the camera. In fact, CCD and CMOs are sensors that create and receive the same color frequency. They send this data as signals to the processor, and the basic structure of the camera is as follows. In this image, you can see the internal structure of a camera, which is the CCD part of the camera. I don't think cameras need a specific definition, and their job is to allow our robot to have real vision. But how many cameras do we use? Are all cameras suitable for robotics? The use of cameras in robotics depends exactly on what you want your robot to do, and what the main structure of the robot's processor board and circuit is, and what it is supposed to be. These determine what type of camera your robot should have, because fortunately there are both cheap, small, and high-quality cameras on the market, as well as professional cameras used for industrial robots. For example, when you want to build a good robot and have a quality camera but not too expensive, you can use this camera model that you see in this image, which is both very high quality and to the point that even semi-traditional robots can be implemented with them, and it is also affordable and easily compatible with different types of processors. And their operating voltage is also low and in the range of 5 volts, which makes these drones a normal ideal for the robotics industry. The normal ideal means that it is a very good and ideal camera that you can use normally and in all kinds of robots. Another type of camera that even has a microcontroller on it for programming that allows you to build an advanced robot is a module called ESP-CAM, which is actually a combination of an ASP-COD micro and a medium quality color camera that are placed together in a pack. And you can use this entire module as the main brain of the robot, which is also connected to its head. And from these pins, it also gives different outputs. For example, you can make a robot that controls a number of motors because it gives outputs from these pins. You can connect these pins to a motor driver so that the robot is seeing and receiving the image of the meter and can move around easily. The next sensor I want to introduce is the optical sensor, which exists in different models that are either made of a photoshell or a photodiode, which generally do the same thing, and that is to detect the intensity of light or the presence or absence of light. But in the following, I want to explain each of these optical sensors better so that you can get to know them better. I will start with the most famous one, which is the photoshell. Well, in fact, a photocell is a variable resistor sensitive to light that has turned this resistor into a light sensor. The photoshell works in such a way that the greater the intensity of the ambient light, the lower its ohmic resistance, and as a result, more current passes through it. And the darker the environment, the higher its ohmic resistance, and as a result, less current passes through it. If the environment is very dark, it will not allow any current to pass through it, and its ohmic resistance will become infinite. This photostyle feature is widely used in robotics, such as light-changing robots or light-detecting robots, or even in solar panels to change the sun so that the panel turns towards the light. There is another type of light sensor called a photodiode, which is different from a photoshell. In fact, a photodiode is a diode that, when exposed to light, generates a very small voltage of a few millivolts. So it somehow generates electricity in a small amount, which is enough for a sensor and the use of this photodiode to sense them. Because by increasing or decreasing the intensity of the ambient light, this voltage produced also increases and decreases. And based on this, we can calculate the amount of light, the amount of ambient light. The main difference between a photodiode and a photoshell is exactly here, that the photoshell never creates a low voltage with light radiation, and actually the voltage. Or it doesn't generate electricity, and it doesn't generate voltage at all, because as it was said, there is a resistor to which the voltage current is connected. And only by shining a light, it allows the current to pass through it. And when it gets dark, it clears the passage of the current. It seems that the photoshell works like this, but in relation to the photodiode, as mentioned, it creates a voltage with radiation and light, and creates a photoelectric difference, and it becomes sufficient somehow. Photodiodes are the mainstay of solar panels that generate electricity using sunlight. The photodiode is a very small component, and therefore its output voltage is also a millivolt, and it uses a sensor. And you can't use this generated voltage in photodiode. It just has to reach an IC to perform the calculations and operations. Here too, when you see the shape of a photodiode and a photosensor, it is quite distinctive in appearance. These sensors that I introduced are single sensors, and to use both sensors, whether photoshell or photodiode, you must design a special circuit, and of course, we will teach you how to design such circuits. But to make things easier for you, component manufacturing companies have come up with ready-made circuits and put them on the market, which are called optical sensor modules. Using these modules has the disadvantage of using an optical sensor module that you see a model and you use it directly and connect it with a minimum of parts, and without the need to build a special circuit for sensors, microcontrollers, ICAs, and various processors, and program them, meaning, for example, you want to connect a sensor to an IC and program that IC to read the light pattern. If you want to use this module, for example, you have to make the circuit of this module yourself because you cannot connect the sensor directly to the microcontroller IC. But when you use the module, this module has its own circuit, which you see here. So, to build the circuit you are building, you can use any cable. That is, you may need to use an empty sensor somewhere and build the circuit yourself. and you may need to use a ready-made module somewhere. Of course, it is recommended that when you want to build a final robot, use sensors without a circuit and customize the relevant circuit for the sensor based on your needs so that it suits your goals and is more professional and versatile, and you are more independent than using a ready-made module. But to conduct experiments and test our theories for building a robot, we can easily use a ready-made module, which I recommend you do too. Because the purpose of the test is just that, and we don't want to build a final robot, but I repeat, after the test, use a sensor with a dedicated circuit board to build the final robot, and you will gradually learn all the things. I hope it hasn't been complicated for you so far, and I will try to present the contents to you in the simplest possible language. So let's move on to the next sensor, and the next sensor that I want to introduce is the gyroscope sensor. The gyroscope sensor is one of the sensors that is mostly used in flying robots, but it is also very useful in non-flying robots. The use of the gyroscope sensor is that it allows you to easily detect the tilt or tilt angle and the position of the robot. You can see one of the most used gyroscope sensors available on the market in this tutorial. The gyroscope sensor is widely used, and a clear example of its use is in mobile phones, which today have all mobile phones with a mouse. Do you want to know what it does in your phone, and how do you know that your phone has it? So when you're playing a car game with your phone, for example, you're playing a car game, you must know that by pulling the phone back and forth, you can steer the car. Or by holding the phone vertically or horizontally, your mobile screen also rotates and is aligned with the horizontal or vertical position. So how does the phone know in what position you hold it and recognize the orientation? Of course, the gyroscope sensor. I think with this example of a phone, you have understood well what the gyroscope sensor is, so you can use it in robots for many different purposes, such as precisely adjusting the angle of the robot's movement, precisely adjusting the angle of the robot's arm, rotating the robot, and the like. You may not believe that humans also have a gyroscope, which is known as the inner ear organ in humans, which does exactly the same thing. When you tilt your head up or down, this inner ear organ transmits the angle to the brain in the form of tiny electrical signals based on your tilt and the gravity of the earth. The brain understands what angle your head and body are relative to theta. Now, if this inner ear organ becomes problematic, you will experience severe dizziness, and in robots too. If this same gyroscope becomes problematic, the robot cannot recognize its own angle and will spin around and move back and forth. The proximity of the gyroscope and the robot was very interesting to you, wasn't it? So, in the introduction, we are talking about the gyroscope and the sensor. When we want to work with it, you will notice it more and more noticeably. But as I said, I am just introducing you here. The next sensor that I want to introduce is the proximity sensor. These sensors are used to detect the environment and objects. For example, when we want to get the shape of a room along with its interior, we can use proximity sensors, which is actually one of the applications that is widely used in robotics. Of course, note that proximity sensing is different from a camera. Well, we can see what objects are in a room with a camera, but in electrical cases, we want to see without seeing. Let's get a sense of what's in the room and the surrounding environment. For example, let's take the room as an example. What's in the surrounding environment? It's exactly like a radar. For example, nearby objects can be identified using a proximity sensor without physical contact. The transmitter transmits the electromagnetic descriptions to the nearby sensor and sends the return signal to the detection direction. And it definitely analyzes, for example. If I want to put it in a simpler language, it is a device that emits electromagnetic waves, such as radar waves, and this he analyzes the waves and finds out based on the reflection. For example, what kind of obstacles are there on the road and around them? What is their size and shape? Exactly is it radar? Therefore, the amount of signal received in the environment can be used to detect the presence of objects, especially nearby objects. The robot can easily use this sensor to detect nearby objects. These sensors are also a way for robots to avoid physical collisions, meaning that the robot now knows exactly what is around it and no longer collides with it, which can be said to be a very useful sensor. Let's move on to the next sensor, and the next most commonly used sensors are microswitches. In fact, microswitches are more of a push button that is used for different parts of the robots. For example, you have designed a robot arm that needs to be driven by a motor and moved a certain distance, and then it stopped. Now, how should the motor and buzzer detect that it has reached the desired location for the teacher? Perhaps using motors such as servo motors and an angular nemesis program, the amount of movement of the buzzer can be adjusted. But this may also have errors, and the arm may move a little more or a little less than the desired amount. Especially if we want to do something sensitive with the arm, the problem will be more obvious. This is where the use of microswitches can be very useful. And then their use is such that the microswitch is placed in the arm or the place where the arm is supposed to move so that when the arm reaches the place, it activates the switch, and this activation sends a signal to the controller, which results in immediate operation. For example, if the controller, which is usually a microcontroller IC, it is defined to hold the arm in place by receiving the microswitch signal. So when the microswitch is pressed by the arm, indicating that the arm has reached its destination, the motor stops and the arm stays in place. And here, you can also see the image of the types of microswitches. For example, in fixed printers, microswitches are used to precisely adjust the nozzle position, and the Swati painter's moving tray is used a lot so that the nozzle and the moving tray are exactly at the desired point. For this purpose, microswitches are used, which are also pictured here. I'm showing you a picture of a microswitch here. A microswitch causes the nozzle to retract exactly to the desired location. It should be set and turned off and on, and not more than that. Why would this nozzle move if this microswitch is not there, or is not working properly? It can't be that when it reaches zero, it actually causes the motor to strain and the device suffers serious damage. You see, automatic microswitches are also very, very important. The next sensor is the touch sensor. Touch sensors are primarily used for touch controls, which have many applications in the robotics industry, such as making touch control panels. Touch sensors, which you can see a few examples of, do not require much explanation, and when touched by a hand or anything that has electricity, they produce an output signal that can be used for various purposes. Another widely used sensor, of course, depends on the type of robot. Temperature sensors are also widely used in the Internet of Things, smart homes, and temperature controllers, apart from robotics. But when you are building a robot that is supposed to work with temperature, then a temperature sensor must also be used. And there are different types of temperature sensors. And for example, robots that are used in environmental conditions to measure the temperature of the environment. Temperature sensors are used in these robots. And now we come to positioning or GPS sensors. These sensors are also very widely used in robotics, and as the name suggests, are used to locate robots, so that the robot can accurately determine its location. Without knowing what path it has taken, how much it has traveled, and where it actually needs to go, it can easily find its path. This is done with the help of GPS sensors. Blue position sensors are divided into two for robotics, one of which is the GPS sensors that receive magnetic signals. The other is a type called magnetic compass that works based on the Earth's magnetic field, and the other is the electronic compass. And the magnetic compass sensor can be used to find the directions of north, south, east, west, etc. in the robotic angle, meaning the robotic is not currently heading north, is currently heading south, is currently heading east, is currently heading west, or even in between. In this image, you can see both a GPS positioning sensor and a magnetic compass positioning sensor, and well, I have a lot of similarities. The next sensor is the accelerometer sensor, which many people confuse with a gyroscope. Some sensors are called compasses, and maybe there is no need to explain much about it, but I will explain it to you. It is better to know that the accelerometer sensor is used to measure the amount of motion and acceleration. What you need to know is that to calculate acceleration, we need to calculate two forces. One is a static force, and the other is a dynamic force. For example, the gravitational force of the Earth, or gravity, is a static force that acts on an object, which is also an object for robot. And now the accelerometer sensor, which also acts like a gyroscope, can help the robot detect how much it is stretched relative to the Earth's gravity. And of course, a gyroscope can do this too. And that's why many people confuse accelerometers and gyroscopes, because in several cases, and at several points, they act similarly. Dynamic force, for example, in robotics, is the force that creates a range of motion to make the robot move forward or fly. Well, when the dynamic force of the motor comes into play to move the robot, in addition to moving the robot, it also creates an acceleration, which is the face of the robot, and at the same time creates a vibration that the accelerometer can calculate this movement and vibrations. Now, where is it of much use? For example, you have designed a robot that is supposed to move on a surface. First, you can calculate this change in the face when you increase or decrease the robot's face. It turns out that if the robot has a lot of vibration on the surface it is moving on, it shows that the surface is very uneven. And this roughness can be calculated based on the vibration and movement of the robot. So you see how much use is the accelerometer in robotics, especially research robots. Inertial measurement sensors are the next sensor I want to talk about. This sensor can actually be said to be a combination of accelerometer, gyroscope, and magnetometer and magnetic compass sensors that allow us to simultaneously measure multiple forces in the form of common data. We can move and obtain and calculate that these sensors are used in very sophisticated robots, such as rescue robots, robots used on planets such as Mars Nora, and such robots that are actually used. Inertial measurement sensors make the robot behave very, very intelligently because, for example, it detects its own tilt relative to gravity and measures this tilt relative to speed and acceleration and detects a positional relationship such as GPS and obtains a perfect position of itself. And for this reason, it can have very precise and skillful control over its movements. And that is why such sensors are used in rescue robots or planetary transformation robots. If a good software program and design is made using inertial sensors, it is possible to design an intelligent robot that moves to a large extent without the need for human control. That is, it does not need to be controlled by a human to move and find its position and perform operations. So you see that it is a very scary sensor. The next sensor is the laser scanner sensor. The laser scanner sensor is one of the 3 sensors that are used to create a spatial map of a place. For example, we want to train a robot to move around a room or a field. Apart from having some kind of sensors, such as ultrasonic or infrared sensors or cameras, it will not allow the robot to collide with anything. But we want to have a robot that has good information about its environment, doesn't just rely on yellow sensors, and has regular movement. It is for such situations that the robot should take a basket image and, in fact, you could say, have some kind of spatial coordinates of its environment. This mapping and imaging is done with the help of a laser scanner sensor. You can see images of several models of laser scanner sensors here. This scanner comes in the form of a rotating laser that fills the surroundings and sends the feedback to the robot in the form of coordinate data. And in this way, the robot has a good map in society. It obtains information from its surroundings, and by combining this data with images such as those from a camera, it can achieve very good accuracy in its movement, identification, and position. So it is one of the important sensors that is mostly used in collecting initial data, but it is also used in real time and continuously in many robots. The last sensor I want to introduce in this video is the current effect sensor, which is a sensor that detects magnetic fields and the intensity of magnetic fields. You can actually see the Hahn effect sensor, the image of which you are viewing, both the empty sensor and the sensor module here, which actually allows us to detect the magnetic field or the intensity of the magnetic field. For example, if we want to use a robot to detect the presence of electromagnetic or natural electromagnetic field, we must use a current sensor. The current sensor reacts to magnetic fields, and if there is a magnetic field in the surrounding environment, it produces output signals, and as the intensity of these magnetic fields increases, the output signals of the current effect sensor increase. For example, you could imagine that as the robot gets closer to a source of magnetic field, it can detect this approach. Of course, you can even build different devices with a current sensor, for example, if you want to know what's actually inside the wall. Is the wiring, for example, voltage carrying? In fact, this sensor is a magnetic field sensor. An electric wire that is buried inside the wall creates a weak magnetic field when there is electricity inside it. This current sensor can detect what I'm trying to do in a separate session, building a device using a current sensor to detect it. I will teach you how to make wire leaves, which will be very useful and useful to you, and I promise to publish this tutorial separately on the channel. This is one of the most important and versatile sensors in robotics. The sensors I have introduced so far are the most widely used. Of course, there are many other sensors, but we have to use the rest based on our needs. Because when a robot needs to do a specific task, we have to look for that sensor. And at the very beginning, we don't need to know all the sensors in the world. So we have provided you with a list of sensors that are most commonly used in all types of robot. Tell me, I hope this session was useful for you. And until the next session, when you want to enter into other topics and introduce different types of robotic software systems, God bless.